Ever stand on a station platform, maybe watching a high-speed train glide in
Yeah.
precisely on schedule?
Yeah.
Or just marveling at the sheer scale of a railway network?
Mm.
Connecting cities, even countries, parts of it built decades, maybe a century ago,
Yeah.
somehow integrated with all this cutting-edge tech.
It does feel like a modern miracle sometimes, doesn't it?
It really does, especially when you think about the absolute need for those systems to run, not just efficiently, but incredibly safely, day in, day out,
Mm-hmm.
often in pretty tough conditions.
Mm-hmm.
How is that level of reliability and, well, peace of mind even achieved?
Mm-hmm.
What are the rigorous processes going on behind the scenes, to make sure everything keeps working without some catastrophic failure?
It is incredibly complex, you're right. And while it might feel like a miracle, it's really the result of meticulous planning, really stringent processes, and a fundamental framework, something that governs every single stage of a railway system's life.
And that framework,
Yeah.
that's exactly what we're dedicating this deep dive to today.
Precisely.
It's known throughout the railway world by a specific acronym, RAMS.
That's the one. RAMS stands for reliability, availability, maintainability, and safety.
Okay.
And it's way more than just, a checklist. It's the comprehensive management process, the structured approach that really underpins the entire railway industry globally to make sure those trains run on time, keep operating when needed, can be fixed efficiently, and critically, keep everyone safe.
So our mission today is to sort of take apart that RAMS acronym,
Yeah.
Understand what each bit truly means in the railway world,
Mm-hmm.
and then explore this incredibly detailed, structured life cycle approach that the industry uses.
Yeah.
Managing RAMs from the very first glimmer of an idea for a new system all the way through to when it's eventually scrapped.
Exactly. It's about getting under the hood, understanding the how behind the safety and performance we just expect.
Right. And this isn't just for, hardcore train designers.
No, not at all. This is fundamental, really, whether you're an engineering student just starting out, exploring transportation, someone building your career in infrastructure, operations, manufacturing in the rail sector, or honestly, even if you're just fascinated by how these complex, safety-critical systems are managed and kept safe, understanding RAMS is key. It pulls back the curtain on the rigor, the planning, the continuous effort that goes way beyond just the physical engineering. It's about the system engineering, the management that makes it all possible.
Okay, good. Let's start then by unpacking that core acronym, RAMS. 4 letters, each one a critical concept. What specifically does each one mean here in railways, and why is the precise definition kind of important?
Okay, let's break it down. First up, we have R for reliability.
Right.
At its heart, reliability is about performance without failure. Specifically for railways, it's defined as the probability that a system or component will do its intended job without failing under specific operating conditions and for a defined period of time. Think of it as the likelihood that something won't break down when it's supposed to be working.
So fewer unexpected stops,
Yeah.
fewer signal failures.
Exactly. Less disruption because components are just doing what they're designed to do. It's about consistent, predictable performance. It's inherent trustworthiness, you could say.
Got it. So that intrinsic ability to just work without failing internally.
Precisely. Now, closely related, but definitely distinct, is the next letter. A for availability.
Quick availability.
Availability is the probability that a system or component is actually in an operational state, ready to perform its function at any given point in time, or maybe over a stated period. So while reliability focuses on avoiding the failures in the first place, availability considers both how often failures happen, that's reliability, and how quickly the system can be put back into operation if a failure does occur.
Oh, okay. So it brings in the repair time.
Exactly. Which leads us straight to the next letter, maintainability. So a system might be super reliable, right? It hardly ever fails.
Yeah.
But if, when it does fail, it takes absolutely ages to fix, well, its availability could still be pretty low because it spends a lot of time out of service.
Right. It's not ready to run, even if it's usually reliable when it is running.
You got it. Availability is about being ready to run when needed. It factors in both unplanned downtime from failures and potentially planned downtime from maintenance, too.
That makes a ton of sense. So a train might have great components, super reliable, but if, say, spare parts are miles away or it takes ages to get a repair crew out after a rare breakdown, the train's sitting there, unavailable even though its parts are technically reliable.
Exactly. You see how they interact. Which brings us neatly to M for maintainability.
Maintainability. So how easy it is to fix.
Pretty much. It's the measure of how easily and quickly a system or component can be restored to operational status after a failure.
Okay.
And it also covers how easy and efficient it is to do scheduled maintenance, like inspections or swapping out parts before they fail.
Ah, plant stuff too.
Yes. Maintainability is about the design characteristics that make repair and upkeep efficient. Is diagnosis straightforward? Are components easy to get at? Do you need loads of specialized tools? Can repairs or replacements be done quickly?
Right.
Good maintainability directly boosts availability because it cuts down the time the system is out of service, whether for fixes or routine work.
Okay, so reliability.
Yeah.
Avoid the breakdown. Maintainability.
Yeah.
Fix it fast if it breaks or needs work. Availability.
Yeah.
The result of those two, the overall readiness.
You got it.
And all three of these seem like they absolutely underpin the fourth letter, which, let's face it, is probably the most critical in railways, S for safety.
Absolutely. S for safety. It's the overarching goal, the most critical element, and it is profoundly dependent on how well the other three perform.
How so, specifically?
Well, in the railway context, safety is typically defined as freedom from unacceptable risks, danger, and injury from a technical failure or error.
Okay. Freedom from unacceptable risk.
Yes. And while, human factors and operational procedures are also huge parts of safety, RAMS specifically focuses on the risks that come from the technical performance of the system itself.
Gotcha.
So think about it. A system that's unreliable might fail in a way that directly causes an accident.
Right.
If a safety-critical system isn't available when it's needed, like a signal that needs to keep trains apart, that immediately creates a safety risk.
Yeah, obviously.
And if a failed safety-critical part can't be quickly made safe or fixed, that's low maintainability, the dangerous condition could hang around longer than acceptable.
I see. So R, A, and M are really the essential pillars holding up S.
Couldn't put it better myself. You simply cannot achieve a high level of safety in a complex technical system like a railway without making sure its components and systems are reliable, available when needed, and can be maintained effectively.
It's so clear how they're intertwined. A failure in one area, even if it doesn't cause a crash right away, could cascade or contribute to a dangerous situation down the line.
Precisely. Unreliability leads to unexpected stuff happening. Low availability means a vital function might be missing when you need it most. Low maintainability means a dangerous state might persist for too long. The whole point of structured RAMS management is to proactively find potential safety-related failures, understand the risks they pose, and then put measures in place throughout the system's lifecycle to either prevent those failures, that's reliability.
Okay.
Ensure the system works when safety functions are required, that's availability, tied to both R and M.
Right.
Or rapidly restore safety if a failure does happen, that's maintainability. The end goal is always to minimize that residual safety risk down to a level that's broadly acceptable based on regulations and the risk criteria set early on.
So it's really not just about responding to emergencies or fixing things after the fact.
No. It's fundamentally about designing, building, and operating systems to stop problems happening in the first place and managing them effectively if they do.
And that proactive preventative angle.
Yeah.
That's why this highly structured approach is so essential, especially in railways. You mentioned the complexity earlier.
Exactly. That complexity is the core reason.
Why is that structure so much more critical for railways compared to, developing an app or even building a car? What's unique?
Well, think about railways. First, just the sheer scale and complexity. We're talking vast networks, huge geographical areas, integrating dozens, maybe hundreds of different subsystems.
Yes. Tracks, powers, signals.
Exactly.
Yeah.
Tracks, civil structures, power supply overhead lines, third rail signaling, and control systems managing train movements, the trains themselves, rolling stock communication networks, passenger info systems, maintenance depots. The list goes on.
And they all have to work together perfectly.
Flawlessly. Second, the long lifespan. Railway infrastructure, trains, they're built to last decades. 30, 40, 50 years, even more.
Wow.
So RAM's performance isn't just about day one. It's got to be managed throughout that entire service life, dealing with wear and tear, things becoming obsolete, new tech coming along.
Okay, that's a big difference.
Third, high safety criticality. Failures can have utterly severe, catastrophic consequences. Loss of life, injury, huge property damage, massive disruption. Safety risk management is just paramount.
Absolutely.
And fourth, the sheer number of stakeholders. You've got infrastructure managers, train operators, multiple suppliers for different bits, maintenance contractors, regulators setting the rules, passengers, freight owners.
A lot of cooks in the kitchen.
you could say that, coordinating RAMS requirements and activities across all these groups, who might even have competing interests sometimes. It's incredibly challenging. Without a universally agreed structured process, managing how subsystems interact, ensuring consistent safety, maintaining performance over decades, proving compliance to regulators, it would be almost impossible.
It really does sound like managing a massive long-term ecosystem with life or death stakes, not just building a product.
It truly is. And this is where the concept of the system lifecycle becomes the absolute bedrock, the fundamental organizing principle for RAMS management in railways.
The life cycle, we touched on it. How does that provide the structure?
The life cycle approach basically mandates that RAMS thinking is baked into every phase of a system's existence, right from the very first spark of an idea or identifying a need,
All right.
through detailed design, manufacturing, installation, commissioning, those years or decades of operation and maintenance, any modifications or upgrades, right through to safely getting rid of it at the end.
So it's a roadmap.
Exactly. A phased roadmap, a clear sequence of activities. It ensures RAMS aspects are planned for, managed, implemented, controlled, monitored continuously. It stops RAMS being an afterthought, bolted on at the end.
So you can't just build the thing and then go, right, how do we make this reliable and safe?
Absolutely not. In fact, the critical decisions made really early on in the first few phases, they have the biggest impact on the final RAMS performance and safety levels, and usually making changes then is the cheapest time to do it.
Ah, makes sense. Fixing fundamental issues later is way harder and costs more.
Hugely more expensive and difficult. And this life cycle idea, it's scalable too. You can apply it to managing the RAMs of one critical component or a whole subsystem like signaling or the entire complex railway network. Same framework.
And this whole process, it's often shown using that V-model diagram, right?
That's right. The V model is a common way to visualize it. Think of a V shape. The left side going down represents the decomposition part, starting high level with concepts and system requirements, then breaking them down into more detail. Subsystem designs, component designs, manufacturing specs.
Top down.
Top down, then the right side of the V goes up. That's the integration and validation side. Bottom up, you take the manufactured bits, put them together into subsystems, install and integrate those into the full system, and then you validate and accept the whole thing before it goes into operation.
And the V shows how things match up.
Exactly.
Yeah.
It highlights how each level of breakdown on the left has a corresponding integration and testing activity on the right.
Okay. And you mentioned there are key processes woven throughout this V model and its phases.
Yes, absolutely. The framework points to three major process areas that aren't just stuck in one phase, but run across much of the life cycle. There's risk assessment, demonstration of compliance with all the requirements, and the practical ongoing stuff. Operation, maintenance, and decommissioning.
And they interact.
Constantly. Risk assessment, for example, feeds into the requirements, but new information you learn during design or operation, that feeds back into risk assessment, demonstrating you've met requirements. That happens at multiple stages, not just one big test at the end.
Okay, let's really get into the nitty-gritty then. This life cycle framework, it's broken down into 14 distinct phases, you said. Walking through these must give a real sense of the rigor involved.
It really does. This is where the theory turns into concrete steps. Let's go through them.
Phase 1, concept, the very start. What's happening here?
This is strategic. You're defining the need, the high-level purpose. From a RAMS perspective, it's about learning from the past and setting the bar for the future. You look at RAM performance from similar projects, historical data on failures, downtime, maintenance effort.
Okay.
You also define the RAM implications of this new idea. How will this new high-speed line or automated metro affect the network's overall reliability or availability? You set initial, high-level RAM targets based on goals and lessons learned.
And for safety.
Similar idea. Review historical safety data from comparable systems. Define the safety implications of the new concept. Does it introduce new interfaces, new ways of operating? And review or define the initial safety policy and overall safety targets based on regulations and company standards.
And general project stuff.
Clarifying the scope, outlining potential solutions, initial feasibility studies, technical, operational, financial, and identifying who the stakeholders are.
So phase 1 is really about setting the baseline, setting the ambition for RAMs and safety, using past experience, defining the what high level, but already thinking how well and how safe.
Exactly. Planting the seeds for the detailed requirements that come later. You establish the intent right away.
Phase 2, system definition and operational context. They're starting to flesh out that concept.
Yep. Getting more specific now about the environment and how it'll operate and be maintained. You do preliminary RAM analysis, still often based on historical data or benchmarks, but you start modeling the expected performance of the proposed setup.
Okay.
You define the RAM policy, the overall strategy for managing RAM through the project and into operation. You identify the expected operating conditions, traffic levels, weather, vibration, and the planned maintenance approach. Depot-based, on-site, condition-based.
Right. How will we look after it?
Exactly. And you identify constraints from existing stuff it has to connect to. For safety, you do a preliminary hazard analysis finding potential dangers based on the concept and environment. Critically, you establish the initial safety plan, how safety will be managed and proven, and define the risk acceptance criteria.
Risk acceptance criteria. That sounds important.
Absolutely fundamental. These criteria specify what level of risk is considered tolerable, acceptable for the system to even enter service. Without these, you don't know what safe enough means.
So you set that safety bar right here in phase 2, before detailed design.
You have to. It provides the target against which all future risk assessments are measured. General tasks here include detailing the system's mission, a more detailed technical description, and refining those operational and maintenance strategies.
Defining those risk acceptance criteria early. Wow, that's huge. Sets the standard everything else has to meet.
Critical. Couldn't agree more.
Phase 3, risk analysis.
Okay, this one's central, it's iterative, and it's incredibly important. You perform systematic hazard analysis and safety risk assessment at the system level.
What does that involve?
It includes hazard identification, finding all potential sources of harm, derailment, collision, electric shock, fire, you name it.
Okay.
Then event identification, figuring out the sequences of events, failures, human errors that could lead to those hazards.
Right.
Then risk determination, analyzing how likely those hazardous events are and how severe the consequences would be if they happened.
Likelihood times severity.
Basically, yes. And a key tool here is the central hazard log. This is a dynamic document, a living record. It tracks every hazard identified, its assessed risk level, the actions taken or planned to mitigate it, and its current status: open, closed, maybe accepted.
And this log starts now and keeps going.
Exactly. Established here, maintained throughout the entire life cycle. Based on the risk level and those acceptance criteria from phase 2, you do risk evaluation and treatment. Decide, is this risk okay as is, or do we need to do more to reduce it? This phase also sets up the process for ongoing risk management.
You stress it's iterative. Why not just do it once here?
Great question. Because risk isn't static. As the design evolves later, as you specify components, build things, integrate them, you might uncover new potential failures or interactions you didn't foresee.
Oh, okay.
New information from testing or even from operating similar systems somewhere else might change your assessment of existing risks. So the risk analysis process runs in parallel with design and implementation. It's a continuous feedback loop.
So if analysis finds a new hazard later on,
or if the assessed risk of an old one goes up, maybe because of a design tweak, you might have to loop back, reevaluate requirements, maybe even rethink design choices from earlier phases to add more risk reduction. The hazard log gets constantly updated. You even reconfirm the risk assessment at the very end of life for decommissioning.
makes perfect sense.
Yeah.
Risk evolves as the system evolves and as you learn more. It's not a snapshot.
Exactly. And the output of this ongoing risk assessment, it directly informs the next phase.
Phase 4, specification of system requirements.
Right. Building on all the analysis so far, this is where you formally write down all the detailed system requirements.
Everything.
Everything. The overall functional requirements, what it has to do. The initial RAMS requirements from phase 2, those high-level targets. And crucially, the new detailed safety requirements derived from the risk assessment in phase 3.
So the specific things needed to reduce those identified risks.
Precisely. The technical or operational requirements needed to get risks down to that tolerable level. You also define the exact criteria for system acceptance. What tests, analyses, documents will be needed later to prove the system meets all these requirements.
Okay.
System-level RAM and safety management plans are firmed up, organizational structures defined. This phase involves deep requirements analysis, making sure everything's consistent, feasible, specifying environmental conditions in detail, defining how you'll demonstrate and accept it, setting up verification and validation plans, and implementing really strict change control.
Why strict change control?
Because changes to requirements at this stage have big knock-on effects. They have to be managed incredibly carefully, assessed for impact on RAMs, safety, costs, schedule, everything.
Got it. So phase 4 translates all the goals, policies, risk findings into the hard technical specs the designers and builders have to follow, laying down the law.
Exactly. These requirements are the foundation for the whole development process that follows.
Phase 5, architecture and apportionment of system requirements.
Okay, now you take those big system requirements and you start breaking them down. This is where you define the system architecture, how the overall system is divided into major chunks, major subsystems.
Like signaling, power, trains.
Exactly. Signaling, power, rolling stock, infrastructure, maybe even further down into components. Then you do the apportionment.
Apportionment.
Yeah. You take the system-level RAM and safety requirements, and you divide them up. You allocate them to these specific subsystems and components.
How does that work?
Well, say the whole system needs 99.9% availability. You can't just assume every part magically contributes equally. You have to analyze the architecture and assign specific reliability targets, maintainability targets, even limits on downtime to individual subsystems based on how critical they are, their predicted performance.
So you give the signal system its own target, the power system its own target.
Precisely. You define the specific RAM and safety acceptance criteria. Each subsystem or component has to meet on its own and when integrated. The system safety plan gets updated to reflect this architecture, this breakdown of responsibilities.
Do you check if this breakdown actually works?
Yes, this phase often involves theoretical demos or modeling, using things like reliability, block diagrams, or simulations to check that, on paper at least, the chosen architecture and the apportioned targets can actually meet the overall system RAMS goals. You're basically distributing the system's RAMS burden strategically.
This is where the detailed technical planning really hits. Not just the system must be reliable, but how reliable the signal must be, how available the power, how fast the brakes must be fixable.
Exactly right. Translating system goals into specific targets for the engineers doing the lower-level design and manufacturing. Defining design constraints based on RAMS.
Phase 6, design and implementation, the actual technical design work.
Correct. Subsystems, components that get designed and developed here, following the detailed requirements from Phase 4 and the apportioned ones from Phase 5. And this phase is packed with RAMS activities.
Like what?
Extensive design reviews, various kinds of analysis, FMEA, failure modes and effects analysis, or FTA, fault tree analysis. These help understand how failures could happen, how they might propagate or lead to hazards. Rigorous testing of prototypes, early builds, assessing the data from those tests against the requirements, planning for how you'll support these systems through life logistics, spare parts, documentation, training needs. Supplier control is huge here, making sure anything you buy from outside vendors meets your strict RAMS and safety standards.
And safety specifically.
Continuously implementing the safety plan. Ongoing hazard analysis and risk assessment based on the detailed design, updating that hazard log constantly, managing supplier safety assurance, and preparing the initial versions of the safety case.
The safety case, what's that exactly?
It's the structured argument, backed up by evidence, that proves the system is acceptably safe for its intended use in its intended environment. It starts getting built here with design evidence.
So RAMS and safety aren't just checks after design. They're baked into the design process itself, influencing choices.
Absolutely. Design is often about trade-offs. RAMS analysis helps make informed decisions to get the best balance of performance, cost, and safety. And yes, the safety case framework gets set up and populated here.
Phase 7. Manufacture. Designs become real things.
Yep, building the components and subsystems. From a RAM perspective, key things are quality control during manufacturing, making sure parts meet spec, maybe doing environmental stress screening, ESS, or highly accelerated life testing, HLT.
What's that?
Basically, you stress components beyond normal limits, temperature, vibration, to try and weed out manufacturing defects or things that might fail early in life.
Shake out the weak ones.
Kind of, yeah. RAM improvement testing might happen too. And crucially, this is typically where the failure reporting and corrective action system, FRAC, gets initiated and starts running.
Fracas.
Yeah, it's a closed loop process. You document failures or incidents, analyze why they happened, root cause, identify and implement fixes, and then check if the fixes actually worked. It's the engine for continuous RAM improvement.
And that starts during manufacturing.
Often, yes. On the safety side, you keep implementing the safety plan, review manufacturing processes for safety issues, use the hazard log, assess any manufacturing data relevant to safety. General tasks are production planning, the actual manufacturing, testing subassemblies, documentation, developing training materials for the physical kit.
That fracas starting early is interesting. You're learning from failures even during production, not waiting until it's installed. That data must be gold.
Absolutely. Data collection for improvement right from the earliest physical stage helps catch systemic issues before they get out widely.
Phase 8, installation, putting it all together in the real world.
This is physically installing and integrating the manufactured bits on site. RAMS activities include having installation procedures that minimize the risk of damage or incorrect assembly things that could mess up reliability or maintainability later.
Right.
You might also start formal training for the operations and maintenance teams, finalize lists for spares and special tools needed based on the design and maintainability studies, general tasks, detailed installation planning, site prep, the physical assembly and integration of all those different subsystems, signals, power, track, etc., into one working system.
Getting installation right seems obvious but critical. A perfect part installed badly is still bad.
Exactly. Installation quality directly impacts the RAMs you actually achieve in service.
Phase 9, system validation, testing the whole integrated system.
This is a massive verification step before anyone formally accepts it. You validate that the entire integrated system works as specified and, crucially, performs according to the defined RAMS requirements in its intended environment.
How do you do that?
This phase includes RAM demonstration. You run the system under realistic conditions, collect loads of data on performance, failures, downtime, maintenance actions, to prove it meets the specified reliability and availability targets.
Like a big soak test.
Yeah, often involves running it for a significant period to get statistically meaningful data. The results get rigorously checked against the RAM acceptance criteria. On the safety side, you validate that the system and its operating and maintenance procedures meet all the safety requirements and that risks are down to that tolerable level. Comprehensive safety testing, simulations, reviews. The application-specific safety case, the one for this specific system in this specific place, gets finalized here based on all the validation evidence.
Okay.
This phase involves formal system commissioning, getting it ready for operation, and often includes a transition or probationary period of running it live, or near live, to demonstrate performance before the formal handover. Training effectiveness is also validated.
So validation is proving, with real data from the integrated system, that it actually hits the required RAMs and safety targets before the owner takes responsibility.
Precisely. It's the hardcore demonstration that the V model worked, that the system built according to the plan actually performs as intended in the real world.
Phase 10, system acceptance, the formal handover.
This is the moment the customer, the owner, formally accepts the system from the supplier or builder.
The sign-off.
Exactly. It involves assessing the results of that RAM demonstration from Phase 9 against the formal acceptance criteria set way back in Phase 4. You also assess the finalized application-specific safety case against its acceptance criteria and regulations.
So checking all the boxes.
It's focused on the formal procedures, generating all the documented evidence needed for it to enter service. The system is formally accepted, brought into operational service, though sometimes a continued probationary period might be part of the deal to get more early operational data.
This is the big, saying, yep, based on the evidence, this system is ready to carry people or freight safely and reliably.
It's the culmination of all the development and implementation work. Signifies that compliance with all RAMS requirements and safety rules has been demonstrated and accepted by everyone who needs to accept it.
Phase 11, operation and maintenance. It's live.
Yeah.
Running day to day. This could last decades, right?
Absolutely. Potentially the longest phase by far. And RAMS management stays critical throughout this entire operational life.
What does that involve?
Ongoing procurement and management of spares, tools, implementing different maintenance strategies, things like reliability-centered maintenance, RCM, and safety-centered maintenance.
RCM?
Yeah, reliability-centered maintenance. It's a structured way to figure out what maintenance an asset actually needs based on how it's used and the RAMS performance you want.
How does it work?
You analyze failure modes, their consequences, and then define the right maintenance tasks, preventative, predictive, maybe even just run-to-failure tests that are cost-effective and keep the system function going. Safety-centered maintenance focuses specifically on tasks needed to keep safety functions working. Operational performance is continuously monitored, that hazard log we talked about. It's actively managed and updated throughout operational life. New hazards, new risks identified in service, they go in. General tasks are just running a railway, following schedules, procedures, and doing the planned maintenance.
RCM sounds smart. Focusing maintenance where it actually matters for reliability and safety, not just fixing breaks or doing checks based on the calendar.
It is. It shifts focus from just stopping equipment failure to stopping functional failure and managing the consequences of failure. Prioritizes maintenance based on criticality. It's very data-driven, often supported by
The system from Phase 12.
performance monitoring.
Exactly. Phase 12, performance monitoring. This is tied right into operation and maintenance, essential for continuous RAMS improvement while it's running.
What happens here? Systematically collecting, analyzing, evaluating, and using performance data and RAM statistics from the live system. This is where that FreightCast system, started way back in manufacturing, is fully used. Recording every failure, near miss, significant event, analyzing root causes, tracking corrective actions.
Okay.
SCADA system supervisory control and data acquisition if they're used. They also provide tons of valuable operational data for analysis.
What are you looking for?
Failure rates, repair times, downtime duration, causes of incidents, how effective maintenance is. Same for safety stats, monitoring accidents, incidents, near misses for trends, potential systemic problems.
And what do you do with all that data?
You use it to check if the system's meeting its operational RAMS targets, identify areas for improvement, maybe need a modification, change the maintenance strategy, more training, and it feeds back into designing future systems too. Lessons learned.
This data loop sounds absolutely vital, proving the theoretical RAMS from design holds up in the real world and driving ongoing maintenance and mods. It's how you prove it stays safe and reliable for decades.
It is the feedback mechanism. Enables continuous improvement, lets operators really understand how their assets are performing.
Phase 13. Modification and retrofit. Things change, systems age, tech evolves.
Yep. And when changes are planned for an existing system, they need the same RAMS rigor as designing something new, just maybe on a smaller scale. You have to do a RAMS impact assessment for the proposed change.
Meaning?
Will this new component affect the reliability of the thing it connects to? Does changing this part make maintenance easier or harder? Could this new tech create new safety hazards or interactions?
You have to think it through.
Absolutely. The necessary RAMS requirements, plans, documents, including the hazard log and safety case, they all have to be revised, updated to include the changes, and you have to demonstrate the modified system is still acceptably safe and performs as needed.
So change control is key again.
Hugely important. A robust change control procedure ensures every proposed mod, no matter how small it seems, gets assessed for its potential impact on overall RAMS and safety before it gets the green light.
Really reinforces that RAMS isn't just a one-time thing at the start. It's alive, it applies whenever the system changes, making sure safety and performance aren't accidentally compromised.
Exactly. Maintaining RAMS integrity throughout the entire operational life through all planned changes.
Okay, finally, phase 14, decommissioning and disposal. End of the line for the system.
Even when you take a system out of service, there are significant RAMS considerations, especially safety. You need a specific safety plan just for decommissioning and disposal. Absolutely. The end-of-life phase has to be managed to prevent risks to people and the public.
So this whole 14-phase life cycle, concept to disposal,
Yeah.
that's the comprehensive, structured roadmap for managing RAMs and railways.
That's the framework.
And woven throughout, as we discussed, are these key concepts that aren't just in one phase.
Right. Risk management, we saw that with the hazard log, the iterative analysis, it's a continuous thread. Starts early, informs design, gets reassessed during operation, right through to end-of-life risks. A parallel process feeding every phase.
And demonstration of compliance. You said it happens at various points.
That's right. It's not just the final acceptance test in phase 10. You're constantly demonstrating requirements are met all through the V model. On the left side, showing the design meets requirements through reviews, analysis, phases 5, 6. Showing manufactured parts meet spec through testing, phase 7. Then on the right side, showing installed subsystems work, then the whole integrated system meets performance and safety goals through validation, phase 9. Culminating in that formal acceptance, phase 10, where you provide all the evidence for operation.
And that evidence can be theoretical or practical.
Both. Simulation reports, analysis results, that's theoretical. Test reports, performance data, inspection records, that's practical. You need both.
All of this must rely incredibly heavily on careful record keeping. Documentation sounds absolutely critical.
Oh, without a doubt. It's not listed as a separate phase, but the need for meticulous documentation, complete traceability, it's implicit throughout the entire process.
What kind of documents?
Requirements, design decisions, analysis results, test plans, test reports, evidence of compliance, the complete hazard log, all versions of the safety case, maintenance records, performance data, all of it has to be documented, managed, maintained.
Why is it so essential?
Demonstrating compliance to regulators. providing the basis for the safety case, allowing efficient maintenance and fault finding during operation, enabling future mods or upgrades. Traceability is key to being able to follow a requirement all the way through and link evidence back to requirement.
And who actually does all this? The framework also mentions people and organization are important.
Yes, it explicitly highlights that for RAMS management to work, responsibilities need to be clearly defined, agreed upon, allocated between the client, main contractor, subs, operators, maintainers, everyone involved.
Okay.
The RAMS process has to happen within a defined organizational structure, using competent people. People with defined roles, the right qualifications, relevant experience, skills, proper training.
So technical engineers, safety engineers.
RAMS managers. And crucial independent roles too. Especially for safety, independent assessment is vital. Roles like independent safety assessors, ISAs. Yeah, independent safety assessors. They're qualified third parties who give an independent judgment on the safety case. Is it complete? Correct. Does it provide convincing evidence the system's acceptably safe? Their independent view is a key layer of assurance. Other independent roles might include verifiers, validators.
So having the right structure, clear roles, highly competent trained people, including independent checks, is just as fundamental as the technical processes themselves. It's about building a safety culture.
Critically so. The best processes mean nothing without the right people and organizational commitment to actually implement and manage them rigorously.
And you mentioned standards earlier. This whole structured approach, the 14 phases, it's all formalized in railway-specific standards.
It is. The processes, requirements, structure we've talked about, they're codified in harmonized railway standards like the EN 50126 series. That provides the overarching framework for RAMS management in railways.
And that helps ensure consistency.
Exactly. These standards give the common language, definitions, required processes the industry follows globally. Ensures a baseline level of rigor, consistency in achieving RAMS and safety across different projects, different countries.
And is this framework set in stone, or does it evolve?
Oh, it's absolutely evolving. Railway tech is always advancing automation, digitalization, new materials, new ways of operating. Standards have to evolve to keep up, incorporate lessons learned.
Any major shifts recently?
Well, one significant evolution that's highlighted is the increasing formal integration of RAM risk alongside traditional safety risks.
RAM risk, what does that mean?
Historically, the big focus was on safety risks, things directly leading to accidents, injury. But there's a growing recognition that reliability and availability failures, even if they don't immediately cause a crash, can still have major consequences. Huge operational disruption, big economic losses like penalties for delays, damage to reputation, and sometimes they can indirectly contribute to safety risks too, like passengers getting off a broken down train onto the tracks.
I see.
So the evolving standards are aiming for a more integrated risk management framework. One that considers the broader impact of system performance failures, not just the ones with direct safety outcomes.
That's a really interesting shift. So the future isn't just about preventing accidents from technical failures. It's a more holistic view, where any significant failure, whether it stops the train safely or not, gets analyzed for its full range of consequences. Safety, operational, economic, wit, all within a structured framework.
Precisely, moving towards a much more comprehensive view of system performance and all its associated risks.
Okay, let's try and bring this all together. We've taken a really deep dive into RAM's reliability, availability, maintainability, and safety. Understanding them not just as separate ideas, but as interconnected elements managed through this rigorous structured life cycle framework, governing railways from cradle to grave.
Right. And this structured approach, following those 14 detailed phases, supported by continuous risk assessment, rigorous proof of compliance, comprehensive documentation, and the work of competent people and independent assessors. It ensures railway systems aren't just physically built. They're designed, constructed, operated to be reliably available, efficiently maintained, and fundamentally safe throughout their potentially decades-long lives.
So for anyone working in or thinking about working in the railway sector design, manufacturing, operations, maintenance, understanding this RAMS framework really sounds invaluable.
It is.
It gives the context, the why, behind so many procedures, documents, analyses, design choices you'll come across. It's not just red tape. It's the systematic process that lets the industry deliver dependable service while holding up the absolute highest safety standards.
Yeah, it's the engine driving both the safety culture and the reliable on-time service everyone relies on. It changes the view from just seeing hardware and software to seeing a managed entity with performance and safety characteristics that have to be actively managed over its whole life.
Right. So here's something for you, the listener, to ponder as you think about the complexities of modern transport. Considering how sophisticated railway tech is, getting automated trains, complex predictive maintenance, and this evolving standard that now explicitly includes RAM risk, covering operational and economic impacts alongside safety, how might this more integrated approach change the day-to-day work, the priorities, maybe even the skills needed for railway engineers, operators, maintainers in the years ahead? What new challenges, what new opportunities might come from treating reliability and availability failures with a similar level of structured risk management as safety failures?
It certainly suggests a future where those lines between pure technical safety, operational performance, and even business resilience get even more blurred, all managed under one single comprehensive risk umbrella.
A lot to think about, definitely. How this foundational framework keeps adapting to the future of rail. Thanks for joining us for this deep dive into the fundamental world of railway RAMs.